Right. Okay, so we're going to pick up on our notes on correlation. We don't have much to go over with this, but just a little reminder, we started talking about bivariate data. Bivariate data is data that has, with every data value, there's two numbers, right? So we can plot every data value on a scatter plot because it has an X value and a Y value, okay? All right, we did a little bit of work with that. I think we left off at the line of best fit, or more importantly called the least squares regression line. You know how to find this on Minitab. Your lab will actually show you how to do that as well. And let's see. When we talk about the line of best fit, remember we always use y hat when we describe the line of best fit. So we never use X and Y when we're talking about the predicted data values, okay? And we actually are able to use the line of best fit to answer some word questions by just like plugging in numbers, okay? So I'm just gonna go to this point here, right below the graph. And this example gives me a question based on the problem that we've been working on so far, okay? The problem we've been working on so far, X represented the square foot of square footage of a house, and Y hat is the predicted value of the price of the house, okay? And we have a least squares regression line that we use Minitab to create, okay? Now this question is asking me to find the average price of all houses whose size is 3,000 square feet. How would I go about solving this question? Yeah, right. 3,000 square feet, that's an X value. So to solve this, it's literally the same thing that I gave above. You just plug in the number and figure out what it is. Okay, so I can go ahead and plug in 3,000 for X. And I don't know why I lost my notes. So I'm going to have to do this by hand. Okay, normally when you solve questions like these, I like to multiply out the number first and write it down so I don't make any mistakes, even though I still make mistakes, but it makes them less likely. 3,000. Okay, so this becomes 160.1939 plus 297.6. Once you're done multiplying, you can just add 160.1939 and it gets us 457.79. Okay. So if I were to have a house that's 3,000 square feet, I would expect the price to be around $457,000. Okay. Any questions on this example? Not too bad, right? Just plugging in for X and figuring out what the number is. Let's do something a little bit harder. Okay. Now, before I talk about how we go about doing questions like this, I'm going to give you well, I'm going to take us back to algebra land for a few minutes, okay? What I have here is I have two graphs. They're actually the graph of the same line. This line is 3x plus 2, okay? And well, the first graph is like more zoomed in than the other one, so let's just focus on the left graph here, okay? Now, just a little reminder, is 3 the slope or the y-intercept? Slope, good. Which means the 2 has to be the y-intercept. Okay, so whatever's attached to the x is the slope. The other number is the y-intercept. Okay, so in algebra land, let's just say I have this line and I choose any 2 points. Okay, so I choose this point and this point. Okay, and what's special about these 2 points is they're right next to each other in terms of x values, right? So if I take a look at how they differ in the x value or on the horizontal axis, they're only one space apart. Does everyone kind of see that? Okay, the way I'm going to write this looks weird, but I'm going to do this. Delta x, delta always means change. So the difference in the x values is 1. Okay, just because, well, they're one x space apart. Okay. Well, I can do the same thing with the y values, right? So I can find delta y, which is the difference in the y values. How far apart are these 2 points in terms of the vertical axis? I think I saw it. 3, right? Because, well, it kind of, well, I just have to go up 1, 2, 3 to get to the next point, okay? So the difference in the y values is 3, okay? Now, the reason it's 3 is because, well, the slope is 3. Okay, So basically, if the difference in the x value is 1, the y value is going to differ by the slope. We're all good with that, right? Eric, do you need the notes from Monday? Okay. Okay, let's jump up a little higher. Let's say I take this point, we're going to stay at the y-axis, and I find 2 points that aren't 1 x value apart, but 2 x values apart. So now they differ in the x values, delta x. Delta x is now 1. Okay. What's delta y now? What's the difference in the height of the 2 points? 6, right? Because if I started at this point and I wanted to reach the other point, I would have to go 1, 2, 3, 4, 5, 6 points to get all the way up to the next point. So this one's actually 6 or 2 times the slope, right? Okay. Oh, I need to move this cursor. There we go. What do you think delta y would be if delta x, oh, sorry, this delta x is actually 2. Sorry, I meant to write 2. What do you think delta y would be if delta x was 3? 9, or 3 times the slope, right? So I think what we're seeing is if the x values differ by any number, to find the difference in the y values, all you need to do is multiply that number by the slope, right? And that actually works in general, okay? So what I have written out here is what the textbook says. I'm gonna change around the definitions here so it doesn't read as confusing, okay? If the values of the explanatory variable is just the x variable. Okay, so if the x values or delta x, if they differ by this amount d, okay, like 1, 2, 3, 4, okay, then the predicted values or the y values will differ by b1 times d. Does anyone remember what b1 stood for? Okay, it actually stood for the slope. Okay, this is the textbook definition. Let me just cross that out and write the slope times d. Okay, so if the x values differ by d, 1, 2, 3 spaces apart, the y values will differ by the slope times d. Let's put that into practice using an example, okay? In this example, we have 2 houses. They're up for sale. One house is 1,900 square feet. The other half is 1,750 square feet. I want to know how their prices are different. Okay, before you do this question, I just want to draw a line in the middle. I'll talk about why I'm drawing a line in the middle, okay? On the left-hand side, okay, using my formula, I guess I would need to know the difference in the x values, right? Let me write that out. Difference in the x values. Remember, by the definition that the textbook gave us, the difference in the x values is actually called d. How would I find that difference in the x values? What's a difference? So I need to subtract. What 2 numbers am I going to subtract? Yeah, right. The 19. Did you see the 1,900 and the 1,750? I couldn't hear what you were saying, but yeah, the 2 numbers that the question gave us, right? All right, let's do the 1,900 or the first price or the first x value, and the smaller x value, 1,750. Yep, I did that. I lost my notes, so I'm gonna have to do this in my own calculator, which means hopefully I don't make a mistake. We got 150. Okay, so D is 150. So that's the difference in the x values. Let's find the difference in the y values, which is really what the question is asking us, right? We want to know how the prices differ, so how the y values differ. What would I need to do to find the difference in the y values? Take a look at the formula. Oh, not 160, but you're reading 160 as the slope because it comes first, but it's actually Okay, let me write this out. So to find the difference in the y values, what Noah's saying, okay, let's just take the slope and multiply it by d, right? What's the slope of this line? Not Noah? Okay. Well, the slope is the number that's attached to the x value, and the slope is 0.0992. I'm multiplying by d, which is the difference in the y values or the x values, which I just found. And let's see what happens when I multiply that together. 0.0992 times 150. It looks like we get 14.88. And that's our answer. All we have to do is take the slope and multiply it by the difference in the x values. Okay. Any other ideas on how to solve this question? All right. Well, let me do this. I'm going to label this the textbook way. Okay. And then I'm going to show you a different way that you can do this question. But I don't know, maybe you guys can catch on as I'm doing this. Okay. So I'm just going to label this another way. Okay. Well, I know the price of the I know the square footage of two houses. So those are the x values, right? That's an x value, that's another x value. So if I plug them in the equation, I should get a y value, right? So why don't I go ahead and do that? Let me do the price of the first house, price of house one. How would I find the price of house one if it's 1900 square foot? Yeah, just plug it in, right? We have an equation. I know what x is. Just plug it in and see what y is. So y hat is 160.1939 plus, 0.0992 times 1900. Okay. Well, I didn't bring my calculator here, so I'm going to use my phone. Okay, let's see. I'm getting 348.67. Hopefully that's right. We'll just say that's right. I have another square footage. I have house two, right? Oh, thanks. I didn't even see you come in. Okay, I know that house two is 1750 square feet. So I can just plug that in for x as well. Okay, so we have y hat equals 160.1939 plus 0.0992 times my other x value, which is 1750. Okay, let's see what we get when we do that. Okay, 1750 times 0.0992 plus 160.1939. Looks like we get 333.7939. Okay. So all I did on the right-hand side is I plugged in my first x value in the equation, and then I plugged in the second x value into the equation as well. So I got two numbers. Well, any ideas on how I would answer the question, the difference in the y values from here? Yeah, I think everyone said it, right? I know the two y values. All I need to do is subtract them together, and then I know the difference in the y values, right? So I'm going to take my 348.67, my 333.79, subtract them together. Let's see what we get. 348.67 minus 333.79. Did not do that correctly. And look, oh, did not mean to do that. Looks like we're getting a roundabout way of getting here. We get 14.88. So we got the same answer, even though we used a different method. Okay. So you're probably wondering, why does the textbook give us one way when we can do it another way? One thing I can think of is the textbook way is actually faster, right? We only did a few calculations with the textbook way. Another thing you might want to keep in mind is sometimes the textbook won't give you the two x values. Sometimes the textbook will just tell you what d is, and then they'll ask you what the difference in the y values is. So sometimes the textbook way is the only way you can do these sort of questions if you're not given what the two x values are. Okay. To me, if you get a question like this, either way works for me. Whichever one you feel more comfortable is fine with me. But you should probably know the textbook way, because sometimes I think on your homework you'll get a question that's worded in a way where the textbook way is the only way to solve the question. Okay. Any questions on this example here? All right, then what we're gonna do is, well, I'll keep this up. We're gonna start a brand new chapter. Let me show you what we're doing today. Okay, I hope I don't give you whiplash today from all the different topics we're covering, but today we're just moving on to a brand new chapter. This is a statistics class, so I guess we have to talk about probability somewhere in here, right? Okay, probability is a very tough subject. It gets very hard very fast. And you know what? We're going to take a slow introduction to probability. We're not going to do anything crazy today. It does get a little crazier later in the semester, but I promise I'm not going to throw you anything too bad. Okay. And the way I like to talk about probability at first is to kind of ease you into it by talking about how probability isn't really that new to you. Okay. Probability, the way I like to think of it is a spectrum. Okay, a spectrum is just something where there's two ends, like good or bad, or high or low, or something like that. But the two ends aren't the only options, right? There's always things in the middle. So, for example, oh, thanks. For example, when we talk about probability, in the English language, usually when we talk about the low end of probability, we say impossible, right? So whenever something is impossible, there's no way something can happen, right? On the other end of the spectrum, we have things that can be described using words like certain or definitely. Okay, these words describe things that are almost like guaranteed to happen, okay? But probability isn't just those two situations. We can have different words to describe different chances of things happening. For example, 50-50, right? Like flipping a coin is 50-50. It's not impossible, it's definitely not certain, but well, there's a 50-50 chance of getting either of the two options. Another example is saying the word quite likely. Okay, if something's quite likely to happen, well, it's definitely more likely than 50-50, but it's definitely not like certain or definitely or sure. Okay. On the other range of things, one thing that people don't really say anymore, fat chance. That's something that's not impossible, but it's definitely not like 50-50. So it's less likely to happen. Okay. Now, mathematicians, we don't like, we want to be a little bit more precise than just using these words, right? So instead, we usually use, you're probably used to seeing percentages. Instead of saying impossible, usually a statistician would say 0%. Instead of saying definitely or certain, a statistician usually uses 100%, right? Okay. Oh, I guess we got 50% in the middle. Okay, probability can be anything between 0 and 100, but we can't get less than 0%, and we can't have probability that's greater than 100%. Okay, so probability has to be between these two numbers, but we can be anything in between. Okay, can't be bigger, can't be lower. Now, in this class, with probability, we rarely ever see percentages. Okay, percentages, I don't know why our textbook doesn't use it. I think our textbook just wants us thinking more mathematically. So instead of 0 and 100%, what's 0% as a decimal? 0, right? What's 100% as a decimal? 1, good. And then of course, like 50% would be 0.5. Okay, I don't know why, but I always get the question before tests, like, what's 100% as a decimal? And it's kind of weird that it's 1, but I guess it works. Okay. Also, fractions, 0, 1/2, 1. These are okay. We usually don't use percentages in this class. Okay. Now, in addition to numbers describing probabilities, we have different ways of saying things mathematically. So mathematicians, we're kind of lazy. We don't like writing out long sentences. So instead, we'll use notation to kind of shorten everything. So let's just say I flipped a coin and I wanted to say the probability of heads is 50%. Okay. Instead of saying that long thing, what mathematicians like to do is instead of saying the probability, we use big P, okay, P for probability. Instead of saying the probability of something, so the probability of something that I'm interested in, we use parentheses, okay? And inside the parentheses is what we're interested in happening, okay? So in this case, we're interested in, well, flipping the coin and the coin landing on heads, right? Now, instead of saying is, mathematicians always use equals. And we don't like percentages, so I'm going to convert 50% to a half or 0.5. Okay. So if you ever see this notation, you just read it as the probability of heads is 1/2. Okay. Any questions so far? Sounds good. Okay. Now I do have some notation I want to talk about. I don't really expect you to like spit out these definitions. I just want you to know that if I use these terms, this is all I mean. Okay. Now, sometimes what I'll do is I'll talk about something that can happen. Like when I roll a die, maybe I want to talk about getting a 6 or getting a 3, or maybe landing on heads or landing on tails. Okay. Whenever I'm talking about something that can happen, I'm going to use the word variable. Okay. And if it's a numerical variable, like 1, 2, 3, something that's a number, I'm going to call it a random variable. Okay. So whenever I talk about like rolling a die or taking a lottery ticket out of the pile and it's a number, I'm going to call that a random variable. Now, I think I've burned this into your heads, but whenever we have numbers, we have discrete numbers and continuous numbers. Remember, continuous numbers can be expressed using a decimal. Discrete are more like counting numbers, like 0, 1, 2, or 3. Okay. In this class, for this set of notes, we're going to focus on the discrete random variable. So anything that can be described using counting numbers, like the number of dogs that you adopt in a month, right? Okay. All right. Don't want to focus too much on that. Let's move on to a definition. Okay. So the first thing I'm going to throw at you is a type of chart. Okay. And this chart is called a probability distribution. Okay. And before I talk about what this is, I'm learning slowly that I should probably take a look at the homework questions before I assign them a little bit more closely. Your homework doesn't call this a probability distribution. It calls it a probability. Oh my gosh, can I spell today? Probability, Jesus. Okay, model. There we go. Okay, so if you go on the homework and you see probability model, just know it's the same thing as a probability distribution. Okay, what a probability distribution is it's a chart. Okay, whenever you hear the word distribution, it's just a chart or a graph. It's a chart that talks about, well, all the things that can happen, and it also lists their probabilities. So it lists all the things and their probabilities that go with it. Okay, but it doesn't stop there. It actually has to follow 2 rules that are kind of like big rules of probability. Okay, and I'll give them to you. Okay, here's the first rule. Okay, now there's going to be a bunch of symbols. Don't be scared. The first one says this: 0 is less than or equal to p of x less than or equal to 1 for every value of x. Anyone want to take a crack at explaining what this means? Ange? Yeah, perfect, right? For everything that can happen, it's saying the probabilities have to be between 0 and 1. Going back to my spectrum, right? When I explain probability as a spectrum, the ends are 0 and 1, right? We can't have a probability that's outside the spectrum. So for example, a probability of negative 0.7 doesn't make sense because it's less than 0. A probability that's bigger than 100% doesn't make sense at all because, well, we can't be 105% certain that something's true, right? That only happens figuratively, right? Okay, so basically all the probabilities have to be between 0 and 1. Nice job. I'll give you the next one. Here's the second property of a probability distribution. Oh my gosh. Okay. This one's a little bit weirder. Uppercase sigma, P of X equals 1. What does that mean? Noah? Good. Was that what you're going to say? Yeah, okay. So I think we're going back to that idea of standard deviation and mean when I had these symbols up. This sum symbol, or gosh, this sigma symbol, it means take the sum, right? So whenever you see this signal, it just means add together, right? So if I read this out, it says add together all the probabilities, and that should equal 1. Okay, so I'm going to write it out. If you understand what this means, you don't have to write this, but the sum of all the probabilities add up to 1. Okay. Now, for something to be a probability distribution, it has to satisfy both of these two properties, okay? Which means if it doesn't satisfy one of these, we don't have a probability model, okay? Let's do a few examples and just see if something's a probability distribution or not, and then we'll come back. So, example 4, I want to decide if this chart represents a probability distribution. We have all the X values or things that can happen up top, and then their probabilities are kind of listed below them, okay? If I want to do this, I should probably check each of the properties. So property 1 says that all the probabilities have to be between 0 and 1. Are all these probabilities between 0 and 1? No, right? There's this guy right there, right? So because, well, one of these probabilities is negative, it actually doesn't satisfy property 1. Okay, so because of the negative 0.30. Okay. Now, if I'm trying to find out if this is a probability distribution, do I have to check property 2 now? No, right? Because if I already know it doesn't satisfy property 1, I already know this is not a probability distribution, okay, or probability model. Okay, I don't have to check number 2 because I already know it doesn't satisfy number 1. Let's do example 5. In this case, I want to decide if it follows a probability distribution. Let's check number 1. Are all the probabilities between 0 and 1? I think I hear some yeses. Wait, there's a negative value here. Does that count? I see a nod, I see a shake. This actually, are you okay? Okay. This doesn't actually count, right? I'm looking to see if all the probabilities are between 0 and 1. That's the second row, right? That means all the X values, this top row doesn't count. Okay, so I don't even have to check the top row. All I'm doing is checking if the bottom row is between 0 and 1. All right, looks like we're good. What would I do to check to see if it satisfies the second one? Yeah, add them up, right? So I'm going to take all my probabilities, the 0.17, the 0.25, the 0.31, the 0.22, the 0.05, and then I just have to add them up. So if I add them together, I kind of cheated. I did this in my office. I get 1. So it looks like it does satisfy property number 2. So we satisfied property number 1, satisfied property number 2. This is a probability distribution. So yes, it is a probability distribution. Okay. Any questions on example 5? All right. I want you to take like 1 minute and work on example 6, mainly because I'm kind of tired of talking, and then we'll come back a bit. Okay, I think I see people finishing up here. Who says this is a probability distribution? Who says no? Nice. Okay, which rule did it not? Well, which rule did it break? Number 2, right? And that's because, well, number 2 says just add up all the probabilities, like 0.3, 0.31, 0.90, and 0.43. That was, I think it was 1.94. Does that sound right? Okay. And that's not 1. So it doesn't satisfy property number 2. So the answer is no, not a probability distribution. Okay. Any questions on example 6? Nice. All right. Let's do a little bit more work with probability distributions. We're going to start this process of combining probabilities together and trying to figure out the probability of a combination of things. But before we talk about that, I want to throw this word out to you. Okay, there's this term called mutually exclusive. Has anyone heard this term before? Anyone know what it means?
That's one thing. The other thing has to be related.
Related or not related? Not related, yeah. So nice job there. So basically, mutually exclusive, if you have two things that are mutually exclusive, it means that they can't happen at the same time. So there's no relationship between the two. Okay. Some examples of mutually exclusive that I like to think about is, for example, winning a game and losing a game. I cannot spell lose. Okay, now we're talking about traditional games where there can only be like a winner and a loser. You can't win and lose a game at the same time, for most games at least, right? Okay. Another example that I thought of is if you take a number, you can't be even and odd at the same time, right? Okay, so even and odd are two things that just don't have an intersection. They can't happen at the same time. Okay. The last thing I can think of is, let's say you're rolling one die. Okay. You can't roll a 2 and roll a 3 at the same time if you just have one die, right? That wouldn't make sense. You can't roll two numbers at once. You can only roll one. Okay. So any of these events are mutually exclusive. So things are mutually exclusive if they cannot happen at the same time. Okay. Now that we know what mutually exclusive means, I can throw you 3 probability rules that we're going to be thinking about for the rest of the week at least. Okay. Let's say I have 2 events. Events are just things that can happen, like rolling a die and getting a number, rolling a heads or tails, something like that. Okay. And I call these events A and B. Okay. So maybe winning and losing, for example. Okay. If these can happen at the same time, which means they're not mutually exclusive, okay, then the probability of one thing or another thing happening is adding up the probabilities and subtracting where they both happen at the same time. Okay, so basically this just happens because we double count them both happening if we add the probabilities together. Now, one thing about this rule is in this class, I'm actually not going to ask you anything about this, okay? This isn't on your final. It's not anything you should worry about. With things that are not mutually exclusive, we won't use this. So we won't use this. Okay. But just know that in the future, when you're thinking about probability, there are cases where you have not mutually exclusive events, things that can happen at the same time, and you use a different formula for that. Okay. Now let's say we have 2 events, A and B, and they are mutually exclusive. So it's like winning and losing, odd or even, rolling a 2, rolling a 3, something like that where they cannot happen at the same time. If you want to find the probability of one thing or another happening, you just add together the probabilities. So it's a really easy rule. Whenever you want to find the probability of this or that, just add together their probabilities and that's it. Okay. The third rule talks about this symbol. Okay, let's say we have an event and I'm going to call it AC. Okay. Does anyone know the name of like this symbol here? Okay, let me spell it out for you. Okay, whenever you see this symbol, you read it as this, A complement. Okay, and it's not like compliment like, hey, I like your shirt. It's more of a compliment like, if you ever heard of complementary colors on a color wheel, they're the 2 colors on the color wheel that are opposite of each other. They kind of like are on the opposite side of the color wheel together. So whenever you talk about the complement of something, you're basically talking about the opposite of whatever you're talking about, okay? So this third rule really talks about when you have opposites of events, event happening or an event not happening. And it's saying that the probability of the opposite event is 1 minus the actual event. Okay, so whenever you have 2 opposites going on, you basically do 1 minus the probability of one to find the probability of the other. Okay, and if that doesn't make sense, let's just do a few examples and I think it'll clear things up. Okay. Let's see this. We have example number 4. We have 4 patients. They made appointments to have their blood pressure checked at a clinic. X is our random variable. It just describes all the things that can happen, okay? X is the number of people that have high blood pressure. And I'm gonna make an edit to this. I'm gonna write exact in this question, okay? Which means that, okay, what 0 means is exactly 0 people have high blood pressure. And one just means exactly 1 person has high blood pressure. And that doesn't include 0. And well, 2 people doesn't include 1 or 0 people having high blood pressure. So each of these are just exact numbers of people having high blood pressure. We have a probability distribution, which lists all the things that can happen, and then the probabilities of each of those things below. Okay, knowing that these events are mutually exclusive, I just told you the answer. Okay, and today's been a long day. Okay, well, can exactly 1 and exactly 2 people have high blood pressure at the same time? No, right? So this question's worded a little bit weird. But basically, the way I worded this question, I won't try to confuse you in other questions in the future. But these things cannot happen at the same time. Okay, so that's how I set up this question. I promise on a quiz or a test, I will make it very clear if they can or cannot happen at the same time. And if you're confused if they can and can't happen, just ask me and I'll tell you, okay? So don't worry about like a weirdly worded question like that, okay? Okay, if things cannot happen at the same time, are they mutually exclusive or not mutually exclusive? Yes, mutually exclusive. Okay, the term mutually exclusive has the definition like that basically is like an opposite. So you're basically doing a double negative when you say something's not mutually exclusive. So this whole idea of mutually exclusive is just very confusing because it's kind of hard to think about like, oh, is it mutually exclusive or not? If I can't happen at the same time, then the answer is yes, it is mutually exclusive. Okay, I get confused about this all the time. I have to think about the definition for a long time before I actually come to a conclusion if it's mutually exclusive or not mutually exclusive. But we'll get there. Okay. Let's actually do some probabilities now. Okay, we have mutually exclusive, which goes with that second rule and the third rule. This time I want to find the probability that X is 2 or 3. Okay, well, let's take a look at our rules here. We have 3 of them. One of them I told you that you don't have to use, so that's kind of a good hint. Which rule do you think I should use for this question? I think I heard it. Number 2, right? Because we have mutually exclusive events. I already told you the first rule we're not using. And this says if I have an or statement in it, I just have to add together the probabilities, right? So let's just apply this rule over here, okay? I know that the probability, I'm trying to find the probability of 2 or 3. Using the rule, this means I need to find the probability that X is 2. I need to find the probability that X is 3. And then all I have to do is add together the 2 probabilities. Okay, so that's all I'm doing here, okay? Now, what's the probability that X is 2? 0.27, right? Because if I look at the X equals 2, the probability is literally 0.27. So I know that. Using the same logic, the probability that X is 3 is 0.08. So if I add these together, looks like we get 0.35. And well, that's the answer to the question. Okay. Now, one thing I want to talk about is I did split up the probabilities here to show you how the rule works. If you just want to skip from this guy, the question, to this, how I got the answer, that's totally fine. I just write out the rule so you can see how it splits up. Okay. Let's do part C. Okay, in part C, we want to find the probability that we have more than 1. Okay. Does more than 1, does that include 1 or does that not include 1? I see some no's, see some yeses. More than 1, that actually doesn't include 1. Okay, so if you say more than a number, you're not including that number, you're just doing everything above that number. Okay, so let me just write a note, does not include 1. Okay, which means, I guess another way to say more than 1 is, well, 2 or 3 or 4, right? That's another way to say more than 1. Okay. Now, if I take a look at those 3 rules that I have on the last page, there's no rule that says, well, if I have 3 things, I can break them up into 3 different probabilities. What do you think I'm going to do here? Yeah, right. Well, the last rule said I can add up 2 things together. So if there's 3 things, I can just add up the 3 probabilities, right? So I'm just going to do that. I'm going to take each of the probabilities, x equals 2, x equals 3, x equals 4, and I can just add up those 3 values. So 2 is 0.27, the probability of 3 is 0.08, and the probability of 4 is 0.01. Okay, and adding those together, we get 0.36. Okay, so it doesn't matter how many numbers there are in the mix. If you're trying to find the probability of one thing or another thing or another thing or another thing, just add up all the probabilities and you'll get your answer. Okay, any questions so far? All right, let's do one more. If I want to find the probability of not 0, what rule do you think I'm going to use this time? The third rule, right? Remember, the third rule tells us about opposites. So whenever you have something that says the probability of not being something, that's a good hint that we're dealing with things that are the opposite of each other, okay? Now, I know that 0 is the opposite of not 0, right? So how would I find the probability of not 0? Perfect. I'm going to take 1 and subtract the probability of the opposite of not 0, which is the probability that x is 0, right? Does that make sense to everyone? Okay, so whenever you see opposites, you just take 1 and subtract off the opposite of whatever you're trying to find, okay? The probability that x is 0 is 0.23. So when I subtract these together, we get 0.77. Okay. Any other ideas on how I could have done this question? Ange?
Could you add 1, 2, 3, and 4?
Yeah, right. That's a good idea, right? So another way we could have done this, and Ange just told me how to do this. Another way of saying not 0 is, well, everything that's not 0, right? 1 or 2 or 3 or 4, right? Well, I know how to do that based on part C. I just take all those probabilities like 0.41, 0.27, 0.08, and 0.01. And if I add those together, well, we also get 0.77. Okay, so whenever you're trying to find the probability of the opposite of something, there's usually 2 ways to go about it. You can do the 1 minus rule, or you can just take all the separate probabilities and add them together to get whatever number that you're looking for. Okay, either one works for me. I would say if you have a really large data set, you probably don't want to do the right method because you're going to be adding up like hundreds of numbers and that's not really fun. But either way is good. All right, any questions on probability?